Hello, everyone, and welcome to Pre-Calculus Algebra Lecture 5. And today we're talking about inequalities. This is an inequality sign, and this is also an inequality sign. This expression means that A is less than B. This expression with the inequality sign means that B is greater than A. A is less than B, B is greater than A. They mean the same thing. Now, I don't hear this mentioned too often, but it's a great rule of thumb to remember. The inequality sign always points to the smaller number. Here, the inequality sign is pointing to A. So we say A, the smaller number, is less than B. Here, the inequality sign is pointing to the A, so we'd read this as B is greater than A, the smaller number. And while both A less than B and B greater than A are correct, we prefer writing it this way. And that's not something that we have to do every time. There will be situations when we write this expression with the inequality sign pointing to the right. But if there's no reason to favor this over that or this over that, we prefer to write it this way with the sign pointing to the left. And the reason that we do is because inequality signs represent or can be represented by points on the x-axis or points on the number line. And if we have two numbers on the number line, like A and B, which of these 2 points, A or B, is the smaller number? Well, we know that A is the smaller number, and why did we come to that conclusion? That we came to that conclusion because A lies to the left of B on the number line. If we have 2 points, A and B, on the number line, the smaller number lies to the left of the larger number. And so typically when we write inequalities, if we have no good reason for writing this in a different fashion, we'll put it such that the smaller number is to the left and the larger number is to the right. It won't always work out to where this is the advantageous way to write it. But if there's no good reason for writing it in a different form than this, we'll write it like this: A, the smaller number, is less than B, the larger number. Just because it coincides with our convention for numbers on the number line. Smaller number A lies to the left of larger number B. Going a little bit further, we may combine two inequalities into one statement. And what does this mean? Essentially, we put this inequality and this inequality together in one inequality. And we put this inequality What we do is we take this inequality, A is less than X, and this inequality, X is less than B, and we put them together in one inequality, like this. A is less than X, that's this thing, and X is less than B, that's this thing. Now let's look at a modification of the inequality sign. This thing means less than or equal to, and here's why. This sign, which we interpret as less than or equal to, is a combination of this thing, less than, and the equal sign. We might think of the bottom half of this inequality sign and the top line of the equal sign being merged into one. Less than plus an equal sign, less than or equal to. Similarly, this inequality is a combination of the greater than sign and the equal sign. Greater than or equal to. Let's work a few examples. First of all, how would we describe this inequality? We'd say, well, what do you think it says? X is less than 3, right? Okay, what about this one? How would we describe what this inequality tells us? 3 is less than or equal to X. This next inequality has two parts. The first part tells us 2 is less than or equal to X. Two is less than or equal to X. What does the second half of the inequality tell us? X is less than 5, right? Looking good. Let's go to the last one. The first half of the inequality, what does it tell us? 1 is less than X. And then we have a second part of the inequality. This part of the inequality, what does this tell us? X is less than or equal to 6. So if you got that, we're doing well. Let's look at a cardinal rule of inequalities. In an expression that is composed of 2 or more inequalities, the inequality signs must all point in the same direction. Here's an example. We have an expression composed of 2 inequalities. 3 is less than X, and X is less than 6. And the inequality signs are both pointing in the same direction. No problem here. But look at the second expression. It's composed of two inequalities. 3 is less than x, and x is greater than 2. The problem here is that the inequality signs are pointing in different directions. That's a no-no. This is no good. That we can't have it. As I mentioned earlier, typically we like to have the inequality signs pointing to the left. It's not incorrect if they point in the other direction, but typically we like to have the inequality signs pointing to the left. But when we have inequalities involving a single variable like x, we read the expression by referring to the variable first. We refer to the variable first. Well, here, that's not a problem. We look at this inequality and we say, x is less than 3. Well, we didn't change anything there, did we? We followed this protocol without changing the way we've been reading this inequality. X is less than 3. But now what about this one? We want to read this and refer to the variable first. So we start off referring to the variable and we say x is, okay, x is what? Well, here the inequality sign points to the 2, so 2 is the smaller number, which means that x is the larger number or the greater number. So if we start this off referring to the variable, we're going to say x is greater than 2. We're going to refer to the variable first, and instead of saying 2 is less than x, which in fact it is, we're going to say x is greater than 2. We're going to refer to the variable first. By the way, both of these expressions are correct. X is greater than 2 is exactly the same thing as 2 is less than x. So why am I making such a big deal out of this? Because when we have a variable in an inequality, we want to refer to the variable first. So instead of saying 2 is less than x, which is correct, I'm going to say x is greater than 2. The reason being that we want the inequality to tell us something about the variable, so we start with the variable first. Now, how would we do this? The first part of the inequality says 2 is less than x, or if we refer to the variable first, we're going to say x is greater than 2. So I'll say x is greater than 2. And now I'll look at this part of the inequality. x is less than 3. In each part of the inequality, I referred to the variable first. X is greater than 2, that's this thing. X is less than 3, that's this part of the inequality. Now let me ask you something. Could I have done this? Could I have said 2 is less than x and x is less than 3? Could I have done that? Yeah. We choose not to because when there's a variable involved, we like to state what the inequality says about the variable first. In addition to representing an inequality using inequality signs, so I guess we'd say we're representing the inequality algebraically. We can also represent inequalities with interval notation and with graphs. Take this inequality. A is less than x, or with reference to the variable x, we start first and say x is greater than a. We take the point A on the number line, and we shade the number line to the right of A, from A all the way to the right. And the interpretation is any real number that lies in the shaded area makes this inequality true. And any real number that makes this inequality true, we would say, is a solution of the inequality. So any real number in the shaded area of the number line is a solution of the inequality. It makes the inequality true. Now, the fact that we have this parenthesis over the real number A this means that the point A itself is not part of the solution set. Excuse me. So if we have this round parenthesis over A, that means that A is not part of the solution set. Now we can also represent this inequality using interval notation. Our solutions lie in the interval from A to infinity. And this round parenthesis to the left of A indicates that the point A itself, or the real number A itself, is not part of the solution. So really this tells us that all real numbers greater than A are a solution to this inequality. Let's look at another example. This exercise is similar to the last one, but not exactly like the last one. Can you tell how this exercise differs from the last? Here we have A is less than or equal to X, or if we refer to the variable first, as we like to do, X is greater than or equal to A. Here's how we represent this on the number line. Since the variable X is greater than or equal to A, X can assume the value of any point on the number line that's to the right of A. If X is any of these values on the number line to the right of A, then X is a solution of this inequality. X is less than or equal to, X is greater than or equal to A. And to show that A is a solution, see, x is greater than or equal to a. So a could be a solution. We have the square brace here instead of the round parenthesis. And this square brace means that the point A on the number line is part of the solution set. And if we represent this inequality using interval notation, I put a square bracket or square brace to the left of A, and this indicates that the number A is part of the solution set. Another example, and we'll just start right off with referring to the variable x. X is greater than A, and x is less than b. So all of these points in the shaded area that lie to the right of A are values that are greater than A. So just looking at this part of the inequality, x is greater than A. All of the number line to the right of A is a solution. Every number on the number line to the right of A is a solution. But our inequality also tells us that x is less than b. So let's find b on this number line. Here it is. Here's b. So the real numbers that are solutions to both parts of this inequality, x is greater than a and x is less than b, are in this interval between a and b. Any real number in this interval is greater than a, and any real number in this interval is less than b. Now, does it say here that x can be equal to a? It doesn't, does it? So I put a round parenthesis here to indicate that a is not part of the solution set. And let's look at that inequality again. Does it say in this inequality that x can be equal to b? It doesn't, does it? So b is not a solution to this inequality either. So I'm going to put a round parenthesis over b to show that b is not a solution to this inequality either. See, neither is part of the solution set. Maybe I should do this. Neither A nor B is in the solution set. Now look at the graphical solution of this inequality. The interval notation solution is going to look a lot like this. We don't draw the number line, but we just have A, B. This is the interval whose left endpoint is A and whose right endpoint is B. And the round parentheses tell us that neither A nor B is contained in that interval. So this represents all of the real numbers between A and B, not including A, not including B. More examples. Another example. With reference to the variable x, we say x is greater than or equal to a, and x is less than or equal to b. The first half of this inequality just this much looks like the number line from a going all the way to infinity. And the shaded portion of the line starts at a and goes all the way to positive infinity. So, and let's see. This inequality says a can be equal to b. It says, I'm sorry, a can be equal to x, or x can be equal to a. X is greater than or equal to a. So because x can equal a, we'll put a square brace here. Now let's look at the other part of the inequality. X is less than or equal to b. And let's find b on this number line. Let's say that b is right here. This part says that x is less than or equal to b. So none of the real numbers on the number line that lie to the right of b are solutions. All of the solutions to this inequality have to lie to the left of b. X has to be less than or equal to b. So none of the number line that lies to the right of b is shaded. Only that portion that lies to the left of b and to the right of a. And this does say x is less than or equal to b, right? So x can be equal to b, and I'll signify that by putting a square brace or parenthesis, a square brace right above the real number b. So we have square brace a all the way to square brace b. And these square braces tell us both a and b are in the solution set. Now, how do we represent this inequality using interval notation? The interval notation mimics our graph solution. We're going to have a and b, and we're going to put square braces to the left and right of a and b respectively. So in interval notation, this represents all real numbers between a and b, including a and including b. Let's do more examples. New example. With reference to the variable, we say x is greater than or equal to a, and x is less than b. The first half. X is greater than or equal to a. So we shade in that part of the number line to the right of a because x is greater than a. And note, x can also be equal to a. So I put a square brace here showing that a is part of the solution set. Now let's look at this part of the inequality. X is less than b. So the elements of the solution set have to lie to the left of b. And notice it doesn't say that x can be equal to b here, does it? It just says x is less than b. So I put an open parenthesis or a round parenthesis above the b, indicating that b is not part of the solution set. So this means that A is in the solution set. But B, with this round parenthesis above it, is not. Now, how am I going to represent this in interval notation? The picture of the graph of the solution, tells us pretty much what the interval notation solution will look like. It tells us what the solution in interval notation will look like. We have an interval from A to B, square bracket to the left of A, round parenthesis to the right of B. So the solutions of this inequality are all of the real numbers between A and B, including A, but not including B. Okay, a couple more examples. The first part of this inequality says x is greater than A. So we shade the number line to the right of A. The second part of the inequality says x is less than or equal to B. So we shade in that part of the number line to the left of B. This part of the inequality says x cannot equal A. So I put a round parenthesis over the A. This part of the inequality says that x can equal B. So I'll put a square brace over B. This means that A is not in the solution set. This means that B is in the solution set. And our interval notation for this inequality, well, it looks just like this, doesn't it? We have A on the left, B on the right, all of the real numbers between A and B, not including A, but including B. Now I have one more example I want to run by you. Okay, feast your eyes on this. X is less than or equal to B. So all real numbers less than B are part of this solution. And this inequality says that x can equal b, so we put a square brace above b, meaning that b is part of the solution set. And our interval notation, well, let's see. We only have b here. And any real number to the left of b is a solution, going all the way to negative infinity. So we'll write our interval notation that way. On your mark, get set, go. Represent graphically and in interval notation. X is greater than 2 and x is less than 3. Okay? This is x is greater than 2, right? X is less than 3. And notice, x can't equal 2 and x can't equal 3, so we use the round parentheses on both. And an interval notation, remember our interval notation mimics what the graph looks like. So all the real numbers between 2 and 3, and we have round parentheses meaning that x can't equal 2, x can't equal 3. Now what about this one? X is greater than or equal to negative 6. So x lies to the right of negative 6 on the number line. And this says that x can equal negative 6. X is greater than or equal to negative 6. So to show that x can be equal to negative 6, we put a square brace there. And to show that x can be any real number larger than negative 6, we let this thing go to positive infinity. Our interval notation will mimic the graph. Square brace next to negative 6. The graph goes all the way to infinity. And so we represent that in interval notation this way. And notice that in interval notation, whenever we have infinity or negative infinity, there's always a round brace next to it, because this is the set of all real numbers that are in the solution set of this inequality. There is no real number equal to infinity. So we don't have a square brace here. We have a round brace, showing that infinity is not part of the solution. Next example, x is less than 5. So on the number line, this is all of the numbers to the left of 5. Any number less than 5 is a solution. So this graph goes all the way to negative infinity. And x can't equal 5. This doesn't say that x is equal to 5, does it? So we put a round brace here. And our interval notation mimics the graph. Negative infinity on the left, 5 on the right with a round brace, showing that 5 is not part of the solution set. One more example. X is greater than or equal to negative 1. X is less than 4. First of all, x is greater than or equal to negative 1. So here's negative 1 on the number line. X is greater than or equal to negative 1. And since x can be equal to -1, we put a square brace here, showing that -1 is part of the solution set. Also, x has to be less than 4. So here's 4. And we put a round brace here to show that x can't equal 4. 4 is not part of the solution set. And our interval solution mimics the graph. -1, square brace, 4, round brace. We have some exercises in our homework that are worded this way. Express each interval as an inequality involving x. What they're really saying is each interval is the interval notation of the solution set involving an inequality in terms of x. So this represents an inequality in terms of x, or this represents the solution set of an inequality in terms of x. Write the inequality. So x can be anywhere in this interval, but it can't be 2 and it can't be 3. Remember, round parentheses. So x can be any real number between 2 and 3. Round brace or round parenthesis means x can't be 2. Round parenthesis means x can't be 3. This is the inequality. This says x can be anything greater than 2 and less than infinity. So in other words, x is any real number greater than 2. So we can write it this way or that way. And the round parenthesis next to 2 tells us that x can't be equal to 2. So this is not greater than or equal to, this is not less than or equal to. It's greater than or less than. X can't be equal to 2. Now compare that to this. X can be any real number between -infinity and 5. So in other words, x is less than 5. Can x equal 5? Yeah. This square brace here says that x can equal 5. That's our inequality. And what about this thing? The set of real numbers between 3 and 5. That means x can be any real number between 3 and 5. So x is greater than 3 and x is less than 5. Can x be equal to 3? Yeah. This square brace says that x can be equal to 3. Can x be equal to 5? Nope. This is a round parenthesis. X can't be equal to 5. This is the inequality that's represented by this solution set in interval notation. Okay, now we start to get to the meat of our discussion. Properties of inequalities, and I'll be more specific. Algebraic properties of inequalities. These are very big in math. The first one, if a is any real number and we square it, we get something greater than or equal to 0. Let's see, if a is 0 and we square it, we get 0. So 0 squared is going to be equal to 0. That works. If a is negative and we square it, we have negative times negative. That's a positive. So if A is negative, A squared is positive. And if A is positive and we square it, we have positive times positive, which is positive. So if A is positive, A squared is positive. What this is really saying is we can't square a real number and get something negative. If we square a real number, it's either going to be positive or it's going to be zero. Our next property, we can add any real number to both sides of an inequality. Here's our inequality. A is less than B. And we're going to add the real number C to both sides. If we take this inequality and add C to both sides, the inequality is preserved. If A is less than B, then A plus C is less than B plus C. And if we turn the inequality around and have A is greater than B, and we add C to both sides, the inequality still holds. In other words, if the inequality is pointing this way, and we add C to both sides, the inequality is still pointing this way. The same thing happens if we subtract any real number from both sides of an inequality. If we have A less than B, and we subtract any real number C from both sides, the inequality still holds. In other words, if the original inequality is pointing that way, and we subtract C from both sides, the resulting inequality still points that way. And if the inequality is pointing the other way, and we subtract C from both sides, the resulting inequality still points that way. So adding or subtracting a number from both sides of an inequality doesn't change the direction of the inequality. If the inequality is pointing this way and we add something to both sides, the inequality still points that way. If the inequality points the other way and we add something to both sides, this inequality still points that way, and so forth and so on. Now, before we list any more properties of inequalities, let's just look at a few examples. Solve the inequality for x. X plus 3 is greater than 6. When we say solve the inequality for x, what we mean is isolate x by itself on one side of the inequality like another. Just like if we're solving an equation for x, we get x by itself on one side of the equation and everything else on the other side. When we solve an inequality for x, we get x on one side of the equation, everything else on the other. So that's what I want to do. I want to get x by itself. And we have this property that says that if we subtract a number from both sides of an inequality, that inequality still points in the same direction. So I can take x plus 3 and subtract 3 from the left and subtract 3 from the right. And this inequality will still be pointing in the same direction. Plus 3 minus 3 is 0, so we just get x on the left. 6 minus 3 is 3. Here's our solution. X is greater than 3. In graphic notation, that's what it looks like. In interval notation, that's what it looks like. Well, this was pretty good. Let's do another one. solve the inequality for x. I want to get x on one side of the equation, everything else on the other. So what I could do is add x to both sides, so I won't have a minus here. So I'll add x. And that leaves me with 8 plus x is less than or equal to 15. I still want x by itself, so I guess I should do what? Subtract 8 from both sides? Okay. 8 plus x minus 8 less than or equal to 15 minus 8. 8 minus 8 is 0, so I'm left with x less than or equal to 7. Ta-da! I solved the inequality. X is less than or equal to 7. And on the number line, it looks like that. X less than or equal to 7. And in interval notation, there's my solution. Okay? More with properties of inequalities. More properties. We can multiply both sides of an inequality by any real number, and the inequality will point in the same direction. So if A is less than B, the inequality is pointing in that direction, and C is positive, then CA is less than CB. The inequality is still pointing in that direction. Okay, suppose the inequality is pointing in this direction. A is greater than B, and C is positive. Then CA is greater than CB. The inequality still points to the right. So if we multiply both sides of an inequality by a positive number, the resulting inequality will point in the same direction. We can also divide both sides of an inequality by any positive real number. So if A is less than B, the inequality is pointing in that direction. A is less than B, and C is positive. Then if we divide both sides of the inequality by C, the inequality still points in that direction. Now suppose A is greater than B. In other words, the inequality is pointing in this direction. A is greater than B, and we divide both sides by C. The inequality still points in that direction. So we can multiply or divide both sides of an inequality by a positive number, and the resulting inequality will point in the same direction. It will point in the original direction. Let's have some examples. Solve this inequality for x. Ooh, we have fractions. I'm not prejudiced, but I hate fractions. I think we all do. But you know what? If I multiply both sides of this inequality by 3, I'd get rid of that 3 in the denominator. And if I multiplied both sides of this inequality by 5, I'd get rid of the 5 in this denominator. So if I multiply both sides of the inequality by 3 and 5, let's see. 3 times 5 is 15. If I multiply both sides of this inequality by 15, I'll get rid of all the fractions and everybody will be happy. So 15 times x minus 3 minus 2 over 5 is greater than 15 times 4. And notice, we multiplied both sides by a positive number, so the inequality continues to point in the original direction. Now I've got to distribute my 15 to both of these terms. So that means I have 15 over 1 times x over 3. And I have 15, or 15 over 1, times 2 over 5, greater than, see, 15 times 4, that's 60, right? Okay. 15 and 3, we got some canceling going on here. 15 and 5, we've got some more canceling going on here. Whoops, 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 whoops. There, that's better. So we have 5x minus 3 times 2 is 6. 5x minus 6 is greater than 60. And remember, I'm solving for x. I want to get x alone on one side. So the first thing I'll do is add 6 to both sides. And I can add any number, positive or negative, to both sides of an inequality, and the direction doesn't change. The inequality is pointing in this direction. If I add 6 to both sides, it will still be pointing in that direction. So I have 5x minus 6 plus 6 greater than 60 plus 6. 6 minus 6 is 0. I have 5x greater than 66. And I want to get x by itself. So I'll divide both sides by 5. And since 5 is a positive number, this inequality will still continue to point in the original direction. I divide both sides by 5. The direction doesn't change because I divided by a positive number. And we do some canceling. And we get x greater than 66 fifths. And I guess an interval notation, here's 66 fifths. And an interval notation, let's see, 66 fifths infinity. Okay, very good. Let's look at another example. Okay, 3x minus 6 is greater than or equal to 3. I want to get x by itself, so I'll add 6 to both sides, and that won't change anything. We can add any number to both sides, and the sense of the inequality will be preserved. It will continue to point in the original direction. So I'm going to add 6. Six minus 6 is 0. I have 3x greater than or equal to 9. I want to get x by itself, so I'll divide both sides by 3. And I'm dividing by a positive number, so the inequality will still point in the original direction. And we have cancel, 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 cancel. That is x greater than or equal to 3. In interval notation, what does this look like? X is greater than 3, or it can be equal to 3, so we put this square brace here. And in interval notation, it looks like that. More properties of inequalities. The major thing that we want to get out of this discussion on inequalities, property number 6. Can we multiply or divide both sides of an inequality by a negative number? It turns out we can. We can multiply both sides of an inequality by a negative number. We can divide both sides of an inequality by a negative number. But if we do, the inequality is reversed. Multiply or divide by a negative number and it turns the sign around. Here we have A less than B, and notice the direction that the inequality is pointing. It's pointing that way. C is negative. We multiply both sides by C. Tell you what, I'll put CA and CB. So I take the inequality A less than B. C is negative. I multiply both sides by C. And look at the direction that the inequality is pointing in now. The inequality is pointing this way. The original inequality pointed to the left, but I multiplied both sides by a negative number, and now the inequality is pointing to the right. It always works that way. And the same thing if I divide both sides by an inequality. Take the same inequality, the sign's pointing to the left, but now I divide by the negative number C, and look, the inequality is pointing to the right. Multiply or divide both sides of an inequality by a negative number, it turns the sign around. Now, did it matter that the sign was pointing to the left? Suppose that the sign had been pointing to the right. A is greater than B, and if I multiply both sides by the negative number C, it's going to turn this sign around to point the other way. And if I take this inequality and if I divide both sides by the negative number C, it's going to take this sign and it's going to turn it around. So regardless of the direction in which the sign is originally pointing, if we multiply both sides by a negative number, or if we divide both sides by a negative number, it takes that sign and it turns it around, and the sign will point in the opposite direction. Now let's look at another example or two. solve for x. In other words, get x on one side of the inequality by itself. I'll just divide both sides by -5. But when I do, I have to take this inequality sign and turn it the other way because I divide it by a negative. And let's see what happens. Cancel, divide both sides by -5, divide top and bottom by -5, and just get x. And I divide top and bottom by -5 here, so on the bottom I get 1. Divide 15 by -5, I get -3. So x is less than or equal to -3. And an interval notation. Wait a minute, this is graphic notation. Interval notation, -infinity, -3, okay. You notice that? I divided by a negative number, and I had to take this sign and turn it around. One more example illustrating this. Solve for x. -x over 3 is greater than 4. I want to get rid of the 3 because I'm a bitter person and I hate fractions. I also want to get rid of the negative sign. So I'm going to multiply both sides by -3. And let me write it this way. Now, are you a bit anxious because of what I've written? You should be. What did I not do here that I should have? I multiplied both sides by a negative number, right? So I should have taken this inequality and turned it the other way. Okay, I turned the inequality the other way. We can breathe easy now. And 3 divided by 3 is 1. Negative times negative is positive. So let's see. I have x less than -12. That's my solution. And in graphing form, -12 here, the round parenthesis indicates that 12 is not part of the solution. X cannot equal 12, but x is less than 12. And in interval notation, let's see, -infinity to -12. And -12 is not part of the solution, so there. That's my solution. Here's a few things that our author calls the reciprocal properties. If A is positive, then its reciprocal 1 over A is also positive. If A is negative, then its reciprocal 1 over A is also negative. So a number and its reciprocal have the same sign. If a number is positive, its reciprocal is positive. If a number is negative, its reciprocal is negative. Now let's compare two numbers. Suppose B is greater than A. Then the reciprocal of A is going to be greater than B. And you know, I don't like the way our book does this. Uh, just remember these two things. If we compute the reciprocal of a number, the number stays positive if it was positive originally. It stays negative if it was negative originally. Um, you know what? If we have an inequality and we take the reciprocals, the number that was the lesser the number that was the lesser, its reciprocal becomes the larger of the two reciprocals. The number that was the larger, its reciprocal becomes the lesser of the two reciprocals. I kind of like that better. If you like this, go ahead, it's not incorrect. But essentially, if A is less than B, the reciprocal of A is going to be greater than B. So maybe what I really want to do is this. Yep, I think that's what I wanted to do all along. If A is less than B, reciprocal of A is greater than reciprocal of B. If A is greater than B, reciprocal of A is less than reciprocal of B. So if A is the smaller number, reciprocal of A will be the larger of the two reciprocals. If A is the larger number, the reciprocal of A will be the smaller of the two reciprocals. Oh, now let's see what we can do with some examples. Well, maybe we should give these another look. If B and A are positive and B is the larger, then the reciprocal of B is the smaller and they're still positive. If A and B are negative and A is the lesser, then the reciprocal of A is going to be the larger. Okay, let's apply this to something like this exercise, which we have in our book. What does it mean when something's raised to the -1 power? Isn't that the same thing as 1 over that thing? Okay. So we have reciprocal. And let's see, if this thing is greater than 10, then couldn't I also do this? 10 is greater than 0, isn't it? So I can just put this right here. Both of these things are positive, so I can take their reciprocals. And the reciprocal of this thing is just going to be 2 minus 5x. The reciprocal of this thing is going to be 1/10. And the sign's going to flip. The larger number here will have the smaller reciprocal. And I'm looking for x, so I'll add 2 to both sides. No, I'll subtract 2 from both sides. Two minus 2 is 0, so I have negative 5x. And holy moly, let's see, 1/10 minus 2, that's the same as 1 over 10 times, let's see, minus 2, that's 20 over 10, isn't it? Okay. So 1/10 minus 20/10 is negative 19/10, okay. And now I need to solve for x, so I'll multiply both sides by negative 5. Now, before I go any further, do I need to change anything? I just multiplied both sides by negative 5, so do I need to change anything here? Like maybe reverse the direction of this inequality? I think I do. I multiplied both sides by a negative, so I have to reverse the direction of the inequality. Cool. Negative 5 times negative 5 is 25. Wait a minute, wait a minute, wait a minute. Why on earth would I want to multiply by negative 5? You know, somebody said when I was little, my mother dropped me on my head. I always thought they were joking, but maybe not. Do I really want to multiply both sides by negative 5 here? I don't think so. I think I want to divide both sides by negative 5. And when I do, I'll switch the direction of the inequality. And I'll take negative 19 over 10. And I'll divide that by negative 5. Yeah. And we have cancel, cancel here on the left. 1, 1. So we got x on the left greater than or equal to this mess. One thing I can, well, tell you what. I'm dividing a fraction by another number. Isn't that the same as multiplying by the reciprocal? So I'll take negative 19 over 10 and multiply by the reciprocal of negative 5, which is negative 1/5. Cool. And this is equal to 19 over 50. X greater than or equal to 19 over 50. That's our solution.